The Kepler Space Telescope only monitors one area of the night sky in the constellations Cygnus and Lyra. The mission has detected an astonishing number of planets and candidates within this small area. Nearly 5,000 confirmed planets have been found. The data show that our solar system is unique due to its stable orbits and nearly circular shape. The majority of Sun-like stars have hot Jupiters or super-Earths orbiting them. The planets are crowded close to their parent stars, and there is no space comparable to the position of our planet in our solar system. New theories of planetary formation based on fierce gravitational interactions and titanic collisions are replacing the old ones. Scientists wonder what violent events formed our solar system and how Earth survived. What can we learn about Earth's unlikely rise from the search for alien planets? Our fascination with the night sky dates back to our earliest days as a species. The endless cycles of the sun and moon, as well as the seasons and years, define our lives and instill a sense of wonder. We began to look for explanations for our observations and for our place in the universe. About 4,000 years ago, the first known astronomers lived in ancient Sumer, present-day Iraq. The gods were identified and their positions were recorded from one season to the next. They were the first ones to divide a circle into 360 degrees and an hour into 60 minutes. The Babylonians used mathematics to track the positions of stars, bringing astronomy to a new level. They developed calendars that were precise and identified constellations. Calendars were developed by various ancient civilizations, including the Babylonians, Chinese, and Egyptians. Understanding seasonal cycles didn't explain how everything fit together, or how we fit into the great cosmos. Greek astronomers saw the planets and stars as part of an ordered universe for the first time. Aristotle, a great philosopher, imagined that the celestial bodies were held in a system consisting of 55 crystalline concentric spheres. Each sphere rotated independently, with its own velocity and direction. This idealized structure provided order to the entire universe and defined the relationship between humans and the gods who occupied the outer spheres. Pythagoras, a mathematician, observed an interesting pattern in the movement of planets. They represented a series of mathematical ratios. Venus is orbited 3 times as often as Mars. Jupiter orbits 5 times as often as Saturn. The music of the spheres was named after these harmonies. However, there were a few discrepancies that needed to be explained. Some planets appeared to change direction, while others seemed to vary in brightness. Claudius Ptolemy, an astronomer who assumed that everything revolved around the Earth, explained the puzzling patterns by creating a model of orbits within orbits, known as epicycles. From our perspective, it appears to move left and then right. Aristarchus, an astronomer from Samos, spotted the flaw in this model. He realized that the Earth revolved around the Sun. This new hypothesis provided a simple reason for Mars's apparent shift in direction. Hipparchus, a respected scientist who felt obligated to defend a geocentric view of the world, rejected Aristarchus's ideas, and they faded away into history. The heliocentric view was not heard again until 18 centuries later, at the dawn of the scientific revolution. By reintroducing the theory, the Polish scientist Nicolaus Copernicus revived the drive for a scientific explanation of the motions of the planets. Johannes Kepler established the laws of planetary motion in the 17th century. He published his book, Astronomia Nova, in 1609, the same year that Galileo was the first to use a telescope, and observed that the planets' orbits are ellipses, not perfect circles. Kepler demonstrated how the brightness of stars can increase or decrease as they move closer or farther from Earth. Kepler, like Pythagoras centuries earlier, was fascinated by what we call resonances, the synchronized relationships of some planetary orbits. Kepler believed that these harmonies showed the perfection of creation. These harmonies were, he thought, created by the ultimate master of geometry, God. Today, astronomers using telescopes, algorithms, and other tools can see that these orbital patterns provide insights into the early days of the solar system. Our solar system is far from a perfect, orderly system. It was created during a chaotic and violent period that coincided with the birth of the sun, resulting in the unlikely survival and emergence of the world we call Earth. All of this began around 5 billion years ago. A dense, expansive cloud of gas and dust existed somewhere in the galaxy at a temperature just above absolute zero. It was cold enough to allow molecules to form. This dense area within the cloud started to collapse slowly inwards. Gas flowed in along a disk as the cloud began to spin. The protostar is formed when the gas releases heat energy as it moves toward the center. As temperatures rise to several thousand degrees Fahrenheit, jets of high speed begin to shoot from its poles. After a few million years, thermonuclear fusion begins in the core. The star's brightness changes during the T-Tauri stage due to intense surface activity, such as solar flares and eruptions. Interferometry is a technique that combines a number of telescopes to create a large observatory. This allows us to observe the irradiated disk of the star, which was once a mere remnant of its formation. The disk starts to change. This is TW Hydrae, a distant star located 176 light-years away. Using ALMA, the Atacama Large Millimeter Array Telescope in Chile, astronomers observed gaps within the disk. This is a sign of planets beginning to form. A planet 16% the size of Jupiter, located 23 times the distance between Earth and the gap's most prominent point, is beginning to form. Another young star, HL Tauri, has several prominent gaps despite being only a few 100,000 years old. According to the standard explanation, the so-called accretion model, planets slowly grow within these disks. The weak electrical attraction pulls together tiny dust particles, some of which are just a few molecules in diameter. Now slightly larger particles begin to collide with each other and grow into small stones. The chemical composition and speed of each rock vary, which causes some to combine while others break apart. As they combine, the velocity of those rocks increases and their chances of shattering increase. The rocks are growing in size. They soon have a large enough gravitational field to attract other stones. When a planetesimal is large enough and located far enough away from the sun so that water can freeze, it will begin to accumulate gas on its rocky core. This is how a Jupiter or Jovian-like planet can be created. A planetesimal that is closer to the sun may turn into a terrestrial world like Earth. The theory states that over millions of years, the protoplanetary disk would change from a cloud of dust and gas into a collection of planetary bodies with different sizes and classifications. This theory does not explain some simple observations. How could Jupiter have formed in such a short period of time? How did Uranus, Neptune, and the outer sparse regions of the disk grow? Why is the mass of the inner solar system so small? The inner region of the solar disk is where the majority of its mass is concentrated. Mercury, Venus, Earth, and Mars are only a fraction of Jupiter's mass. Recent observations led astronomers to adopt a new model for planetary formation and a radical story about the birth of our solar system. The ALMA Observatory captured a disk around the star HD 142527. Astronomers studied the density differences from one end to the other of the disk. As the disk rotated, spiral arms appeared, similar to those found in a spinning galaxy. These waves of density have the effect of pushing some pockets of gas and dust out toward the outer edges. These clouds can quickly condense out there due to the lower temperatures. This doesn't explain the formation of the terrestrial planets or the strange distribution of planets within other solar systems. Kepler has helped astronomers identify over 5,000 extrasolar worlds. Some of them are unknown types, such as hot Neptunes. These dense bodies are the remnants of gas giants whose atmospheres have been ripped away by stellar winds. There is also a large class of rocky worlds called super-Earths. These are up to 10 times larger than our planet. Most of them are alien to our solar system, being gas giants that orbit near their stars. Some of them are so closely packed to their stars that they take just days or even months to complete an orbit. Gravity would have drawn these giants inward from farther away. Scientists believe that the solar system wasn't immune to such dramatic movements. According to a new theory, this occurred over a period of 600,000 years through a series of events called the Grand Tack. The story begins in the early stages of solar evolution. The core of the solar nebula could have been the place where a super-Earth formed. Jupiter formed around 3.5 times Earth's distance from the Sun when nuclear fusion was ignited in its core. Later, the planet would have lost its angular momentum due to interactions with the disk of the Sun and moved inwards to a position that is similar to Mars. This threw out the balance of the entire solar system. As Jupiter moved inward, it snatched up rocks and planetesimals. Others were thrown into a frenzy of collisions that shattered them. These collisions reduced a large part of the inner solar system's mass to dust and small stones, which would then have drifted into the Sun. Had it not been for a series of unrelenting collisions, a hypothetical super-Earth might have met a similar fate. The Sun would likely have consumed it. The inner solar system is relatively clear of gas and rocks due to the chaos of these collisions. Jupiter then experienced a change and began to move away from the inner solar system. Mean motion resonance, a gravitational interaction, propelled Jupiter outward. Saturn fell into an orbit that was 2 to 3 times the distance between Jupiter and Saturn when it formed. Over time, the two planets interacted gravitationally with each other and moved further away from the Sun. The inner solar system had a new start as its remaining mass was ground down into tiny fragments, and the formation of terrestrial planets restarted. The result was a new group of small terrestrial planets: Mercury, Venus, Earth, and Mars. The Grand Tack theory goes beyond the conventional understanding of solar system evolution, suggesting the creation of these small, rocky planets. Early terrestrial planets formed not only by growing, but also attracting excess hydrogen, helium, and volatile compounds such as methane, carbon dioxide, and other volatiles. The atmospheres of these first-generation planets were 1,000 times denser than Earth's, rendering them uninhabitable due to extreme surface temperatures. Earth, a second-generation planet, formed with a comparatively thin and shallow atmosphere, resistant to overheating but substantial enough to sustain moderate temperatures. Earth developed into a habitable world hosting over 8 million distinct species of animals and plants, along with countless other species over the course of its history. It's astonishing to comprehend that the complexities of the universe can be described with mathematical and physical functions. We now understand that a solar system like ours is the product of myriad events ranging from the collisions of dust particles to the formation of Jovian planets. The culmination of these events led to the formation of our solar system through a series of events including a giant planet moving towards the Sun, mass loss in the inner solar system, and the formation of a new generation of terrestrial planets, including Earth. We ponder whether Earth's story is common or unique in the cosmos, as our knowledge about the universe continues to expand. Astronomy today is characterized by layers of unanswered questions that continue to deepen. We persist in our efforts to decode the formulas and calculations that govern the ever-evolving cosmos.